Hello and welcome to The Space Above Us, episode 164, Space Shuttle Flight 82, STS-82, No Trouble with Hubble. Before we get started, I wanted to give a quick reminder that, at least at the time of this recording, it's worth keeping an eye on the show's Twitter feed, at Space Above Us. I generally try to avoid making time-sensitive announcements or references on the podcast itself, since a lot of people listen to the show months or years after the fact. So, the Twitter feed is the best way to stay up to date with what's going on. It's especially handy if I have to make tweaks to the show's schedule, such as unexpectedly slipping by a week, which I definitely mention for no reason in particular. I also post photos and sometimes video for each episode. Even if you don't use Twitter normally, you can read it without an account, twitter.com/spaceaboveus. Check it out. This will especially be fun when Twitter goes bankrupt in 2026 or something and I get to confuse future listeners. Anyway, last time, we wrapped up our coverage of the somewhat bonkers NASA 4 mission. We seem to be hitting a sort of dark middle chapter of the Shuttle Mir program, but for the fourth time, a NASA astronaut was able to successfully complete their mission while living and working aboard the Russian space station Mir. The relationship between the American and Russian space programs has always had its ups and downs, and we're clearly in a down phase right now. But that just means that an up has to be right around the corner. Well, eventually. In the meantime, I think we can find some things that are unambiguously great right now. For example, Space Shuttle Discovery is back. Did you miss it? Because the last time we saw good old OV-103 was 12 flights and 18 episodes ago, back on STS-70. On that flight, Discovery became the last shuttle to deploy a TDRS satellite, with the following generations of the communications satellite network hitching a ride on expendable rockets. Since then, Discovery has been enjoying a well-earned break while undergoing some extended maintenance and upgrades. Among other enhancements, Discovery now has a spiffy new exterior airlock. The new airlock is basically the same idea as the old one, but instead of being inside the middeck with its external door flush with the aft bulkhead of the crew compartment, it now sits in the very front of the payload bay, with a short little tunnel connecting it to the middeck. The result is a setup that's a lot more conducive to docking with space stations, while also freeing up a considerable amount of room on the middeck. As of this moment in the narrative, Discovery can't quite dock with space stations since it's missing the orbiter docking system that will go on top of the new airlock, but don't worry, that's coming. And to clear up a misunderstanding of my own, I should mention that they did not just move the interior airlock to the outside. The external one is new. The internal ones would hang around for a while, but I believe they were ultimately scrapped. Oh, and if you're thinking to yourself, wait, isn't this supposedly new external airlock basically what Atlantis has for Mir? The answer is, sort of. With Atlantis, there is indeed an external airlock, but the internal airlock is still there too. Additionally, the external airlock is a couple meters further back in the payload bay, to accommodate concerns about clearing Mir structure during docking that were ultimately solved by the docking module. But eventually, Atlantis will get the same external-only treatment as Discovery. While Discovery's new airlock won't be connecting to any space stations anytime soon, it's still going to get one heck of a workout on this flight. That's because for the second time, we are rendezvousing with the Hubble Space Telescope for a series of upgrades. Just like the last time on STS-81, this mission was always part of the plan. The Hubble was specifically designed to be serviced by the shuttle every once in a while, for maintenance, orbit boosting, and so that it could benefit from the latest and greatest in telescope technology. For those of you who have built your own PCs, the operation will be very much akin to upgrading your RAM, GPU, and other easily swappable components. But instead of something that costs a couple $100 and fits into your hand, it'll be something that costs $100 million and is the size of a refrigerator. And speaking of the latest and greatest in technology, it's time for another round of something that really amuses me for some reason, highlighting the difference between space tech and consumer tech. I just think it's cool looking at how the timelines in different areas of technology don't always align how people expect. Similar to how viewers around the world experienced Neil Armstrong's epic-defining first small steps through a black and white 480-line interlaced image of a slow-scan TV signal, space nerds of 1997 could follow the advanced space telescope servicing STS-82 on the internet, but a very different internet than folks know today. First, this was back when people still distinguished between the World Wide Web and the Internet, which are in fact different things. So the press kit points out how interested parties could visit http://spacelink.msfc.nasa.gov via the World Wide Web, anonymous FTP, Telnet, and Gopher. Don't bother checking though, because I'm way ahead of you. Spacelink.msfc.nasa.gov is down on the World Wide Web, FTP, Telnet, and Gopher. Yes, I installed a Gopher client just to check. Fun fact, where the web has websites, Gopher apparently has gopher holes. Oh well. If anyone is daring enough to try the dial-up modem line, the number is 205-895-0028. But onwards to more relevant matters. Just like the previous Hubble-related flights, we've got an entire orbiter full of spaceflight veterans here, so it's familiar faces all around. Commanding the mission was Ken Bowersox. When we last saw Bowersox, he was commanding STS-73, the US Microgravity Lab 2 mission. But before that, he was the pilot on STS-61, so this will be his second trip to Hubble. This is his fourth spaceflight, and he's still got one more to go, but since that one will be a long-duration ISS mission, this is his last time at the helm of an orbiter. Joining Bowersox at the front of the flight deck was today's pilot, Scott Horowitz. When we last saw Horowitz, it was on STS-75, as he peered through the window at TSS rapidly fading into the distance on the end of its broken tether. Here's hoping that today's mission goes a little better. This is Horowitz's second of 4 flights. Behind Horowitz, we find Mission Specialist 1, Joe Tanner. When we last saw Tanner, it was under similar circumstances as today, in that he will also be paying close attention to astronomy equipment in the payload bay. But that time it was the Atlas III payload on STS-66. Today he'll be heading out into the payload bay for himself on this, his second of 4 flights. Sitting in the middle of the flight deck is a familiar face that we haven't seen in quite a while. Mission Specialist 2, Steve Hawley. We've known Hawley for so long that when we first met him, he was flying on STS-41D, Discovery's first flight, and now he's back for its 22nd flight. When we last saw him, he was delicately easing the Hubble Space Telescope out of the payload bay on STS-31, the Hubble deploy mission, back before any of us cared what spherical aberration was or knew how Perkin-Elmer built reflective null correctors. After that flight, he decided to change things up a bit and headed over to NASA Ames, which is more research-oriented. After a couple of years, he felt the pull of operations again and returned to Johnson as the Deputy Director of Flight Crew Operations, a role once filled by, among others, Deke Slayton. He had hoped to maybe fly in space again, but didn't feel it was appropriate for him to push it, so he just focused on the task in front of him. But when the time came to find a deft robot arm operator who was also an expert on the Hubble, why, what's this? It's Steve Hawley, the guy who used the RMS to deploy Hubble in the first place. And he's an astronomer. So, after taking a day to consult with his family, Hawley accepted and found himself once again training for the exciting ride uphill. And I guess he still didn't get it all the way out of his system, because he'll be back one more time, making this his 4th of 5 flights. Moving down to the now roomier middeck, we find Mission Specialist 3, Greg Harbaugh. When we last saw Harbaugh, it was on STS-71, the first Mir docking. But before that, he featured in the STS-61 episode when he almost had to take over for Story Musgrave due to some nasty frostbite. Harbaugh had trained as a backup for STS-61, so he knew the telescope inside and out, making him a perfect EVA candidate for this mission. This is his 4th and final flight. Joining Harbaugh on the middeck was Mission Specialist 4, Mark Lee. His inclusion on this EVA-heavy mission makes a ton of sense, since at this point he was the chief of the EVA branch of the astronaut office. When we last saw Lee, it was on STS-64, where he and Carl Meade took turns trying out the Simplified Aid for EVA Rescue, or SAFER, which, as of this recording, was the last untethered EVA. He'll be heading outside one last time on this, his 4th and final flight. And last but certainly not least, we have Mission Specialist 5, Steve Smith. When we last saw Smith, it was on STS-68, where he joined friend of the show Tom Jones in scanning basically the entire planet with a sophisticated radar system for the Space Radar Laboratory 2 mission. I'm sure he's looking forward to the fact that on this flight, instead of just peering out the window, he'll actually be heading outside on this, his 2nd of 4 flights. Before we move on to the launch and begin this mission in earnest, it's worth taking a moment to consider something that Steve Hawley pointed out in an oral history interview. When the STS-81 crew arrived at Hubble and began tearing pieces out of it, nobody questioned it, since the telescope was not working as intended. As we know, it was actually working quite a bit better than people really gave it credit for, even with the optical flaw, but still, it was essentially broken. This time is different though, since everything is working fine. Sure, there are some components that are showing some signs of wear, but the Hubble was working great and had been ever since 1993. So you really have to ask yourself, is the reward promised by the upgraded equipment currently sitting in Discovery's payload bay really worth the risk of removing perfectly functional components? Well, once again, this is one of those situations where I'm going to pose a question where you'll likely assume the answer is yes, and then I sort of anticlimactically do say yes, but still, I wanted you to actually think about it. Hubble was designed to be upgraded, and we have a very focused and experienced crew who has trained for a long time and is supported by an army of engineers and technicians on the ground. But despite the motto that Gene Kranz came to embrace, failure is always an option. How would the scientific community and the general public react if NASA decided to upgrade a perfectly good telescope and then proceeded to biff it up? Probably not very well. So I guess we better get this right. We'll be starting this mission off with a bang, but unfortunately it was a loud bang emanating from the mobile launch platform as Space Shuttle Discovery slowly made its way out to the launch pad. A 7-meter-long crack suddenly appeared in the massive steel structure as it supported the orbiter, both SRBs, and the empty external tank. It turned out that the platform, which was first used for Apollo 10, was not seriously damaged, and the shuttle was perfectly fine, but it was still pretty freaky. Once Discovery safely made it to the pad, though, there were no major issues, and the launch itself proceeded nice and smoothly, with no unscheduled holds, lifting off on February 11th, 1997 at 3:55 and 17 seconds a.m. Eastern Standard Time, and soaring through an uneventful ascent. One minor item to note as a flight dynamics nerd is that there was about a 2 meter per second underspeed at main engine cutoff, requiring the rendezvous to be slightly replanned. But as I have learned in excruciating detail at my day job on OSAM-1, that's pretty typical. As the crew settled in for the multi-day chase of the orbiting observatory, it's worth noting that it wasn't the only space rendezvous underway. The day before Discovery lifted off, Soyuz TM-25 also ascended into orbit, carrying Vasily Tsibliev, Sasha Lazutkin, and Reinhold Ewald. 31 hours or so into STS-82, the Soyuz crew docked with Mir, and, well, you already know that side of the story. I also just want to congratulate Reinhold Ewald for somehow getting mentioned on 3 episodes of this show, despite his short spaceflight career. STS-82 flew pretty much the same rendezvous profile as STS-61, the first servicing mission, but changed it up a bit for proximity operations. STS-61 had opted for an inertial approach, executing a sort of big swooping backflip, passing in front of Hubble by a couple hundred meters, and then looping back. On STS-82, Ken Bowersox used a plus R-bar approach, now familiar from the Shuttle Mir missions, cruising on up the imaginary line between the Hubble and the center of the Earth. One benefit of this change was that with an R-bar approach, there's a sort of natural braking effect, which meant that fewer thruster firings were required. It also meant that Discovery could switch to the low Z thruster mode at a range of around 450 meters instead of the 120 meters we saw on the previous servicing mission. For the capture, and really for the entire mission, Steve Hawley was the one at the controls of the remote manipulator system. In an oral history interview, he described some of the finer points of operating the arm, demonstrating why he was a great pick for such a crucial role. He said that one pattern to avoid is making a series of small inputs, one after another. That causes the arm to move, then stop, then move, then stop, and this can build up an oscillation that makes life difficult. Instead, Hawley preferred to make even smaller inputs, but did it continuously, slowly correcting any errors and getting closer and closer to his target. I guess there was something to his technique after all, because with no difficulty, 47 hours and 38 minutes into the flight, the Hubble Space Telescope once again found itself on the end of Space Shuttle Discovery's robot arm. Half an hour later, it was berthed onto the flight support system, which would allow the crew to rotate Hubble along its long axis as needed. I'm pretty sure I mentioned this the last time we were here, but it's just too neat to skip. Fun fact, the FSS is the same support structure that we used to hold on to the Solar Max mission way back on STS-41C. Waste not, want not. On Flight Day 4, all was ready for the first of 4 planned EVAs. Mark Lee and Steve Smith were already in their EMUs, getting ready in the shiny new external airlock, and things were going great. But as they began to depressurize the airlock down to 5 psi, the crew were in for a nasty surprise. Suddenly, right before the eyes of Steve Hawley and Joe Tanner on the flight deck, the Hubble solar array above the port side of the orbiter began to rotate. Fast. Far faster than was typical. In what was clearly an uncommanded motion, the array slewed from being mostly horizontal to being mostly vertical before banging into the stops and bouncing back around 40 degrees. Hawley and Tanner looked at each other, aware that this was potentially a very serious problem. Most sources didn't mention how long this took to play out, but Ben Evans put it at around a minute. So while it might not have looked super dramatic to you at first glance, that's really moving for a spacecraft solar array. Tanner reported it to the ground, who spent the next hour or so deciding what to do, before finally deciding to proceed with the EVA. According to Hawley, the motion was dramatic enough that if it had been caught on video, the ground surely would have scrubbed the spacewalk. While Lee and Smith worked, the ground figured out what the likely cause of the problem was. When the airlock was updated, so was the position of its exhaust vent. Turns out that, unnoticed by anyone, the new location was right underneath the Hubble solar array, and they had essentially blasted it with a big puff of air. Whoops. Oh well, everything remained in working order, so I guess this one was a freebie. On this first spacewalk, the plan was to perform the 2 most important upgrades, installing STS and NICMOS. The Space Telescope Imaging Spectrograph, or STS, was a big 318 kilogram box about the size of a fridge, which came equipped with a 2-dimensional detector. This would allow it to gather 30 times more spectral data and 500 times more spatial data than the instruments that were currently operating in Hubble. This new sensor was especially helpful for studying the dynamics of gas and stars around galactic centers and the supermassive black holes that lurked unseen inside those centers. Both STS and the other instrument we'll be talking about came with its own set of corrective optics, meaning that they didn't need CoStar to help fix the slightly out-of-focus light coming from the mirrors. Eventually, all of the instruments would have these corrective optics, and CoStar would be able to come home and free up a slot for another instrument. Joining STS was NICMOS, the near-infrared camera and multi-object spectrometer. This is another big heavy box about the size of a fridge, and just like a fridge, it prefers to be cold. That's because of a key word in the NICMOS acronym, infrared. With this upgrade, Hubble would edge its capability down out of visible light and into the top part of the infrared spectrum, unlocking a whole new way to examine the universe. Since infrared instruments need to be nice and cool, and since unlike JWST this won't be hanging out at L2 with a big giant sun shield, it brought its own method of chilling out, a dewar of solid nitrogen, designed to last for 5 years. I also wanted to mention that somewhere in its inner mechanisms is both a grating and a prism, which have been combined into something called a grism, which I just think is a fun word. NICMOS would allow Hubble to peer inside clouds of cosmic dust to see how stars and planets are formed, while also studying warm objects that don't emit much visible light, like brown dwarf stars. Alright, now that we've introduced the new instruments we'll be installing and freaked out Hubble's solar array, it's time to finally actually get to work. On Flight Day 4, Mark Lee and Steve Smith became the first people to exit Discovery's new external airlock as they began a long day on the job. That external airlock actually made their lives a little easier, since embedded in the truss-like structure that mounted the airlock to the walls of the payload bay was a new tool storage compartment. Which is good, because once you count up all of the various custom tools, extensions, tethers, crew aids, and such, you end up with a list of over 300 items. For the first spacewalk, Mark Lee would be free to move about the payload bay, while Steve Smith locked his feet into the end of the RMS so that Steve Hawley could move him around. The first major task was to remove the Goddard High Resolution Spectrograph, or GHRS, and the European-made Faint Object Spectrograph, or FOS. The GHRS had served the science community well, but only had a one-dimensional sensor as opposed to the fancy new two-dimensional one we'll be installing in a couple of minutes with STS. Plus, it jumped the gun a little bit and shut itself down a few days before Discovery even launched, so it's a good thing that the crew was already on their way to replace it. With the GHRS out of the way, the crew were free to install NICMOS, which was inserted with no difficulty, and it remains there to this day. Though there was one little asterisk to mention about NICMOS. At some point, the pressure exerted by the solid nitrogen chiller caused its dewar to expand just a little bit, bringing it into contact with some stuff that it was not supposed to be in contact with. The result was that heat was able to cross this little unexpected connection and slowly warm up the nitrogen just a little bit faster than expected, causing it to run out in only 2 years instead of 5. Bummer. Don't worry, we'll fix that on another flight. Next, it was time to install the replacement for the Faint Object Spectrograph. FOS, which astronomer Jonathan McDowell notes was his favorite Hubble instrument since it generated, quote, loads of delicious data on the ultraviolet spectra and continua of quasars, had complemented the Goddard high-resolution spectrograph, but it was time for it to return to Earth. In its place, STS, the Space Telescope imaging spectrograph, was slotted into its now empty instrument bay. And just like NICMOS, STS remains there to this day. Both of these instrument installations went smoothly, but it was one of those things where people who are mega experts on a topic make an incredibly difficult thing look easy. Imagine trying to slot a big cardboard refrigerator box into a hole that is only about 13 millimeters, or half an inch, wider than the box. This already isn't easy. Except now imagine that you have to hold the box directly in front of your face, so you can't really see where you're going. And you're going to do this while standing on a skateboard that's being pushed around by a friend who's moving the skateboard according to your instructions. This is basically what Steve Smith had to do here. In order to accomplish this delicate task, all 4 EVA crew members and Steve Hawley, who operated the RMS for all of the mission spacewalks, put a lot of time, energy, and practice into developing a robust communication protocol. Because remember, all that training isn't just about learning how to move the instruments around the payload bay or how to operate the robot arm. It's about learning how to work effectively together as a team. So here are some of the rules that the crew came up with that allowed them to be so effective. First, only the astronaut on the end of the arm could give Hawley instructions on where to move the arm. This allowed the free-floating astronaut to give directions to the astronaut on the arm without creating an ambiguous situation for the RMS operator. For example, if Lee, as the free floater, said down, down, left, Hawley would know that Lee was asking Smith to move the instrument down, down, left. The only exception to this rule was that the free-floating astronaut could call stop, and the RMS operator would stop. Hawley explained that this was important since the free-floating astronaut had a much better view of what was going on when the astronaut on the arm had a, quote, face full of instrument. Second, the astronaut on the arm would typically give movement requests in the coordinate system of the shuttle. That is, they would request to be moved port, starboard, aft, forward, and so on. But if they were in a situation where they couldn't really see the shuttle anymore, such as with their head inside an instrument bay, they would explicitly state that they were switching to body coordinates. Then they could request movements like head up, feet down, left and right, all from the astronaut's point of view. Third, the crew wanted to avoid a situation where the astronaut on the arm wanted to be moved, but a lengthy conversation was happening between the shuttle and the ground, tying up the communications. To avoid this, they developed hand signals that Hawley could see out the window and react to, making use of every precious moment outside. And lastly, this was all made possible due to extensive integrated training. Unlike the last time Hawley flew, he was now able to practice his RMS inputs with his EV crewmates actually out on the end of a simulated robot arm in a neutral buoyancy pool. This resulted in more realistic training that allowed everyone to practice using these coordinate systems and hand motions. The result was a graceful and efficient dance where Hawley could anticipate the needs of the EV crew, and everyone kept working quickly, accurately, and safely. Pretty cool. But there is one little wrinkle here. Hawley joked that all of this robot arm coordination led to the question of who really installed the new instruments. The EVA crew would say that they, of course, were the ones who did it, but Hawley says, no, you just held on to them while I moved you around. So really, I did the installations. Well, whoever did it, the two new instruments were safely installed, and after 6 hours and 42 minutes in the payload bay, Lee and Smith were back inside. The next day, it was time to suit up and do it all over again, this time with a new EV crew. Floating free this time was Greg Harbaugh, and on the RMS was Joe Tanner. Not wanting to repeat the dramatic solar array movements seen before the first EVA, the airlock depressurization procedure was slightly altered. Among other things, some vents were covered with, I kid you not, gray tape, aka duct tape. This forced the system to vent slower than it would normally, so escaping air wouldn't disturb the Hubble. Once out there, the order of the day was to replace a few pieces of support equipment. First up was a fine guidance sensor. This is an optical instrument that, as the name implies, helps with precision pointing, but also contributed science of its own via astrometry, measuring the positions of the stars. One was starting to show signs of wear, so it was swapped out for a replacement. Next, one of the engineering and science tape recorders was swapped out with an identical spare. The spare was the same as the old design, so we'll still have to wait another day to meet the fancy new upgraded alternative. And lastly, some optical control electronics were also swapped out, but I don't know much about it, so I have nothing fun to say. One slight cause for concern was raised during the course of the spacewalk. Harbaugh and Tanner noticed that the multi-layer insulation, or MLI, the silvery foil wrapping around the telescope, was starting to degrade on the side that typically faced the sun. There were a bunch of little cracks, and it was starting to delaminate a bit. This wasn't necessarily a major crisis, but it wasn't great either, so the ground got to work on some potential fixes. After 7 hours and 27 minutes, the crew headed back inside. After only 2 EVAs, the minimum success criteria for the mission had already been met, so everyone could breathe a little easier. While Harbaugh and Tanner wait for the airlock to repressurize, let's check back in on Hawley's oral history for another perspective from the RMS operator. The interviewer said, quote, "I imagine having someone out there on the end of the arm, and you're basically responsible for not only the Hubble and the equipment and everything else, but a human life." Hawley replied, "Yes, by then you've probably so insensitive to all that stuff. I mean, by now you've launched and you've grabbed the Hubble, so you're just like, whatever." And then he laughed. Oh, how quickly the magic fades. Another day, another EVA, as on flight day 6, Mark Lee and Steve Smith headed back outside for the second time. For this spacewalk, they swapped their roles, with Lee now on the end of the arm and Smith free to move about. The first task was to replace a data interface unit, or DIU, with a spare unit that had been upgraded. Similarly, later in the spacewalk, a reaction wheel assembly, one of the mechanisms that pointed the Hubble where it wanted to point, was swapped with a refurbished spare. You might be wondering what the difference is between an upgraded spare and a refurbished spare, and unfortunately, so am I, because I've got nothing. In a less ambiguous upgrade, one of the engineering and science tape recorders was replaced with a fancy new solid-state recorder. The old recorder, which stored science data as well as information about the state of the telescope itself, used an old-fashioned reel-to-reel tape system storing about 150 megabytes of data. The new system stored 10 times that, 1.5 gigabytes, and had no moving parts. These days, just about everyone benefits from massive amounts of solid-state storage in their phones and computers, but 1.5 gigabytes was no joke back in 1997. With 10 times the storage and infinitely fewer moving parts, it was a great upgrade. While we're out here, this is also a good opportunity to introduce a new tool I believe will be sticking with us straight through the entirety of the Shuttle program and into the ISS era today, the Pistol Grip Tool, or PGT. The PGT was one of 3 very similar types of tools that were all essentially high-tech power drills. What made these drills fancy was that they had some very specialized bits and extensions to handle the task at hand, but could also be configured to address a particular problem. For example, let's say you wanted to turn a bolt with a precise amount of torque, or you only wanted to turn it exactly 3.5 times. I'm sure that with some practice and experience, the crew could get pretty close, but why add the extra risk? Instead, the Power Ratchet tool, the multi-setting torque limiter, and now the Pistol Grip tool were available to use. To be honest, just reading the top-level descriptions provided by NASA, these tools sound nearly identical, but I'm sure that as always the devil's in the details. One major difference is that the Pistol Grip tool was smaller, designed for more precision, and was controlled by its own microprocessor. Developed based on EVA crew feedback after the first Hubble servicing mission, it's an upgraded iteration on the previous tools. Considering that they're still using the PGT, and I haven't heard of the other two tools before, I feel pretty comfortable calling the upgrade a success. As they wrapped up the EVA, Lee and Smith took a closer look at the degraded insulation on the telescope. They also took things one step further and tested how well some Kapton tape would stick to the outer layer of the insulation, which could potentially allow for the easy installation of some patches over the damage. Unfortunately, the tape did not adhere very well, and so the easy solution was out. After 7 hours and 11 minutes in the payload bay, Lee and Smith closed the airlock hatch after another successful EVA. On flight day 7, it was time for the 4th consecutive day of spacewalking. Harbaugh and Tanner donned their spacesuits and headed out into the payload bay for another day of work. First, they installed a refurbished unit of the solar array drive electronics, which, as the name implies, controls the movement of the solar array. In a fun little twist, this particular unit had actually been returned home from Hubble on STS-81, then refurbished, and now here it is back again. They also rode the RMS way up quote-unquote above the payload bay to the top of the Hubble, where they installed some new covers on top of the old magnetic sensing system. As you recall, on STS-61 a new MSS was installed, but it was observed that the coating of the old system was flaking off, which could potentially interfere with the telescope. The STS-61 crew fashioned some suitable temporary covers out of some spare insulation, signed their names to the inside using a marker, and then slipped the covers on top of the old MSS. Well, now that we're back again, the crew has brought along a more permanent cover to take over for the temporary one built by the STS-61 crew. Don't worry though, since the new covers went on top of the old ones, the old crew's autographs are still there. While at the top of the Hubble, Harbaugh and Tanner installed some insulation patches over the MLI that had the most damage, so there were still some homemade tech solutions up there. They also grabbed some samples of the damaged MLI so folks could better understand the nature of the problem and come up with a better permanent fix. 6 hours and 33 minutes after heading outside, Harbaugh and Tanner sealed the airlock hatch, and the 4th of 4 planned EVAs was complete. Finally, on flight day 8, as you may have guessed from my repeated use of the word planned, we do have one unplanned EVA. After hearing about the MLI damage during the second EVA, the ground had been working on a solution. Partway through the mission, a 5th spacewalk was approved, and instructions for a makeshift insulation patch was sent up to the crew. When Lee and Smith headed outside for the last time, they carried with them insulation patches for 3 critical areas of the observatory. Again, author Ben Evans gets us some extra detail, describing how the patches were made out of spare insulation, Kapton tape, parachute cord, and alligator clips. When we started the shuttle program, I never would have predicted just how often the crew would be called upon to perform our little space-age arts and crafts. But I guess the popsicle sticks, pipe cleaners, and GIMP did the trick because the handmade insulation was successfully installed. Oh, and in case you're wondering, yes, the STS-82 crew totally signed the patches with markers, adding their names to the growing list of autographs hanging out somewhere on the Hubble Space Telescope. After 5 hours and 17 minutes, the crew headed back inside. And that's it for the EVAs. Over the course of 5 consecutive days, the crew worked through an incredible 33 hours and 11 minutes of spacewalking, all with no serious issues and with all mission objectives completed, and then some. The next day, Steve Hawley had one more job to do with the RMS. He moved the end effector over to the grapple fixture on the telescope, raised it up out of the payload bay, and 7 days, 21 hours, and 45 minutes into the mission, released it as Space Shuttle Discovery carefully backed away. The crew left Hubble in a slightly better orbit than where they found it, since after each EVA except the first, they had performed long and gentle reboost maneuvers using the small vernier attitude control jets. Each burn had lasted around 20 minutes and had imparted 1 or 2 meters per second of delta V to the orbiter and the telescope. Though somewhat hilariously, this was a clear case of what I call secret metric. The mission report talks about burns that were 3.3 feet per second, or 6.6 feet per second, which just so happens to be 1.0 meters and 2.0 meters per second, respectively. Clearly, the flight dynamics team was using more civilized units under the hood. In all, the reboosts added up to a 15-kilometer raise for Hubble, counteracting slow altitude losses due to atmospheric drag. And speaking of atmospheric drag, it's time to experience a whole bunch of it as we return home. Bad weather at the Kennedy Space Center delayed re-entry by 1 revolution, but it was maybe a fortuitous delay. The new entry profile just so happened to take Discovery and its crew directly over Houston in the middle of the night. Capcom told them that as the orbiter tore through the atmosphere overhead, leaving a plasma trail in its wake, they lit up the entire sky, and that the view was pretty impressive. Commander Bowersox replied, "It was a pretty good view from here too." Discovery touched down at the Kennedy Space Center and rolled to a stop, racking up a total mission duration of 9 days, 23 hours, 37 minutes, and 7 seconds. After a rocky start, the Hubble Space Telescope wasn't just working, it was working better than ever. And with its new upgrades, it would continue to peel back the mysteries of the universe year after year, a shining testament to the power and promise of human spaceflight. Next time, we'll pack Space Shuttle Columbia full of science equipment and embark on one of the shortest shuttle flights of the entire program. There's just one problem though, it was supposed to be one of the longest. Ad Astra, catch you on the next pass.